So this is the third and last part of lesson 1. In the previous 2 parts, we saw some examples of algorithms that take either a linear amount of time, linear with respect to the input size of the problem, or a polynomial amount of time. Now we will look at a couple of different classes of running times. One of them is sublinear, meaning that these algorithms run faster than linear time algorithms. And we'll also see examples of exponential time algorithms, meaning algorithms in which the running time increases exponentially fast with the size of the input. So let's start with a very basic algorithm that I'm sure you have seen in more introductory courses. It's called binary search, right? And you can use it when you search for a given number in a sorted array of numbers. So the inputs to this algorithm are the array of the, let's say, n numbers, which is sorted, and the number, let's call it p, that you are searching for in that array. So let's look at an example. Suppose that this is my array A. It has 9 elements, and suppose we are looking for the number 5, or actually let me make it 3 so that it is a number that we cannot find. So we start in binary search from the middle of the array, and because the element at the middle is larger than p, the number we are searching for, we will now ignore essentially the upper half of the array, because we know for sure that all of these numbers are larger than what we are looking for. And so we will only search now in the next iteration the left half of the array. So this is the important aspect of binary search, that in every iteration we're throwing away half of the remaining elements of the input. So again, here we're searching for p. We start from the middle. In this case, the middle, you can pick whether you will define this as the middle or that as the middle. Let's say that this is our middle. So you compare p with -1. P is larger than -1. So you ignore this part of the remaining array, and you only focus on this part, which is again only half of the elements that you had in the last iteration. So you again compare p with the middle of this array, which by convention may be the element 2. So p is larger than 2, so you only have to compare now in the last iteration p with the last remaining entry, which is 5. Of course, they're not equal, so you know for sure that the array A does not include the number p that you are looking for. How long does this take? Again, we're thinking in terms of upper bounds here. So we have a number of iterations, right? In every iteration, we are we're throwing away half of the remaining inputs. So totally, the number of iterations will be upper bounded by the ceiling of the logarithm base 2 of the input size n, right? Of course, times a constant. The constant, as usual, represents the amount of work we need to do in every iteration, which is independent of n. In this case, we have to make a comparison, right, in every iteration. So this is why we refer to this algorithm as a logarithmic time algorithm. Okay, let's now switch to merge sort, which is a very well-known algorithm for sorting an array of n numbers. So we call merge sort in each of the 2 halves of the original array. AL prime is the sorted version of the left half, and AR prime is the sorted version of the right half. And then the only thing we need to do is to merge these 2 sorted arrays. But remember from the first part of this lesson today that merging two arrays of size n that are already sorted can be done in a linear time, proportional to the size of these two arrays. So now the question is, how many iterations do we need to perform here of this complete algorithm? So in every iteration, we split the input array into two arrays of half size. So if we start with n elements initially, we will have at most log base 2n iterations of this recursive procedure, right? So the running time eventually will be upper bounded by the number of iterations times the amount of work that we need to do in each iteration, and that work is to essentially merge two sorted arrays. But that can take a linear amount of time, right? So this is why I will write here times n times constant. So we end up with a running time which is the product of the logarithm of n times n. This is why we refer to such algorithms as log linear or linearithmic time algorithms. In the second part of the lesson today, we talked about the independent set problem, giving you a graph of n nodes and a constant k. And I was asking whether there is an independent set of nodes of size k in that graph. Suppose now that I don't give you a specific value of k, I'm asking for the maximum size independent set that you can find in the graph. For example, suppose that the graph looks like this. What is the maximum independent set in this graph? If you think about it, you can include in the independent set this node, this node, this node, this node, and this node. These are 5 nodes, and they form an independent set because none of these 5 nodes is connected with another node in this set. So how would you write an algorithm to find the maximum independent set in a general graph of size n? So here is an algorithm for solving this problem. It checks every possible subset of nodes. So given that we have n nodes, how many possible subsets of nodes do we have? As you may remember from combinatorics, if we have a set of n things, there are 2 to the n possible subsets of those n things. For example, if n is 3, the possible subsets are, for n equal to 3, we have these 8 possible subsets. Now, the algorithm considers each possible subset S and asks whether that set is an independent set. How much work is involved in checking that, given that any of these sets can be at most n elements? To check whether any two nodes are connected by an edge, it would take at most n squared operations. So the number of iterations of this for loop is 2 to the n, and within each iteration of the loop we need to do at most this amount of work. So the running time of this algorithm is upper bounded by n squared times 2 to the n times a constant. Now, of course, the term that increases faster here is the exponential term, and that's why we call this algorithm an exponential time algorithm. Now that we have seen an algorithm that takes an exponential amount of time, you may be wondering if there is anything that is even slower than that. So consider the traveling salesman problem. What happens here is that we're given n points, think of them as n cities in a map, and we're also given the distances between any pair of these points. And we need to construct a minimum distance tour that visits every point exactly once. So imagine that you are a salesman and you have to visit all of these n cities. You should visit every city exactly once in your tour. And you want to find the tour in which you will have to do the least amount of driving, right? So you have to find the minimum distance tour. At the right figure, such a tour that visits every city exactly once. Now, how would you solve this problem? If you apply a brute force approach, right, you can say, I will consider all possible tours, and I will try to find the one that has the minimum distance. How many possible tours are there? If we have n cities, n points, for the first point in our tour, we have n choices. For the second point, we have how many choices? N minus 1, because 1 is already taken. For the third point, we have similarly n minus 2, all the way to the nth point of the tour. For that one, we are left with only one choice, actually. So if we look at the total number of possible tours that we can create with these choices, the number of tours, the number of possible tours is n times n minus 1 times n minus 2 all the way to 1. This is what we call n factorial. So the running time of such an algorithm that enumerates all the possible tours, would be upper bounded by n factorial times a constant. Of course, n factorial, as you know, increases even faster than an exponential function of n. So I mentioned this as an example of an algorithm that would be what we call a super exponential running time algorithm. So now let's wrap up this lesson. We have seen a number of different algorithms and we have evaluated the running time of each of these algorithms. This table tries to put all of this in a more practical context. Suppose that we run these algorithms in a processor that can execute 1,000,000 instructions per second. That's pretty reasonable. What we see is a column for algorithms that would take a linear amount of time, log linear. Log linear, remember, is something like merge sort. Linear is something like finding the maximum number in a list or merging two ordered lists. N squared would be an algorithm that finds the closest pair of points. N cube, remember we talked about finding disjoint sets. Here we have a couple of columns for algorithms that take an exponential amount of time, and you see what happens when we change the base slightly from 1.5 to 2. And we have also algorithms that take super exponential, such as n factorial, for instance. So for algorithms that are linear, log linear, perhaps even quadratic, even when you increase the size of the problem significantly from a few tens to a few million, the running time still remains quite reasonable, right? You can do this. Even if you have to wait for a few days, you will get your answer. When we get to algorithms, however, that take an exponential amount of time, or even more than that, then even for relatively small problem sizes, such as 100 input elements, right, it will take years to give you an answer. What this means in practical terms is that when we have an algorithm that takes an exponential amount of time, or faster than that, essentially we don't have a solution for that problem. We don't have an algorithm that we can use in practice. This is why in computer science, and especially in the study of algorithms, we're trying very hard to find algorithms that are in this category, that they take either a linear, log linear, or perhaps polynomial amount of time with respect to the input size. Now, I have to emphasize again that even if the algorithm takes a polynomial amount of time, sometimes it is still not an algorithm that is practical, because depending on the size of the problem and depending on the exponent here, we may still get solutions after a prohibitively long time. In the next class, I will introduce you to some notation, the big O, big omega, and big theta notation. These are very useful mathematical tools to argue about the running time of algorithms. They allow you to focus on the asymptotic running time of the algorithm as the input size becomes very large, without having to worry about insignificant constants or terms that are not the dominant terms in the running time.